Okay. Our speaker today is Patrick Ferris. Patrick was an undergraduate at Cambridge and was then did an RA with Anil and Forsi. He's now doing a PhD. And on that, he's going to talk about what kind of problems he wants to solve with his PhD. So I think I'll leave him to it. Thanks very much for doing this talk. It's all yours.
Yeah, very much. Thank you for having me. I think, first of all, I'd like to put a few caveats. If you were there at the presentations on Wednesday, the Climate and Sustainability Research Showcase, a lot of this is going to sound very familiar, and I apologize in advance. If you were at Michael's talk last week, a lot of this is going to sound very familiar, and I apologize in advance.
That's good, so I won't explode.
That was just the nature of it, unfortunately. But I think some of this will be different, and there'll be a lot more reflections on why some of these problems are happening. The last little bit of context is that this is, in some ways, a draft for a conference talk that I'll be giving in 2 weeks at a conference called Undone Computer Science in France, which is looking at all the kind of reasons why certain areas of research in computer science have been left undone, which could be political, or economic, or all sorts of other reasons. This talk is primarily looking at maybe why some of the problems that we're encountering in climate science with computer science have been left undone. So thank you, Ketchum, for the introduction. Patrick, first year PhD student here in the department and for the Energy and Environment group. I did my undergrad here and also worked as a research assistant here, and I've worked in a research company here. So I'm very much familiar with the computer science department. So the talk is mainly organized into 3 kind of primary areas. A lot of it is to do with uncertainty, which we'll look at and try and define a little bit what we mean by that, but how then this relates to different areas of computer science, and finally to ecology. We'll look at the context in which myself and a lot of colleagues have been working in the ecological space. And then finally, we'll look at kind of reflecting on why some of these problems happen, and maybe start thinking about some solutions to some of these problems. And so to begin with, I want to talk about scientific methodologies in the computational age. So previously in experimental science, scientific methodologies were quite constrained and had finite resources, and looked at things like maybe observations through telescopes and these sorts of things that were easy to reason about. And then with the computational age coming along, a lot of these things got increasingly more complicated, which has both good benefits and also a lot of negative problems as well. And we're looking at it in the context of geospatial work. So this means looking at maps, this means looking at machine learning, lots of programming languages like Python and R, satellite imagery, lots of data formats that are geospatial specific, large data sets, small data sets, uncertain data sets, and all of these things all coming into the computer, and then hopefully some results coming out the other end. Or in a majority of cases, we run out of memory and have to deal with that as a problem. But what do we mean kind of by uncertainty? Uncertainty in our case is actually not really the uncertainty that a lot of people think about in terms of ignorance in a methodology. So for example, a lot of kind of the scientific methodology is looking at, there are some things that we're ignorant about and we would like to become less ignorant about. And hopefully via the scientific methodology and by doing experimental science, we can start to get a grasp on this. The problem is, especially with computational age in computer science, there's a certain amount of uncertainty that is now inherent in just the computers that are involved, the data that's involved, and how we manage on a human level all of this data and computation within pipelines, within our computers, within clusters, and sharing data amongst ourselves, whether that's by email or a USB key or some kind of Google Drive or things like this. So the context in which I've been working and a bunch of colleagues is a project with plant scientists and zoologists in the department, in the University of Cambridge. And we've been looking primarily at how do we assess additional carbon within avoided deforestation projects in the tropical moist forest region, which is a lot of words. But basically what we're trying to do is look at a project and decide whether there's still trees there and whether that has been additional in relation to the rest of the country, or at least a region that we decide we're allowed to match against. So the visualization's on the screen. On the left, we've got a graph showing the difference in the amount of carbon stock within a project and outside the project, and the green zone is additional carbon. which is a great thing for an avoided deforestation project. On the right, we've got a visualization of some of the methodology behind this, which is counterfactual pixel matching, which allows us to take pixels within a project, the green points, and match them to other areas within the country, the blue points, and then decide whether the carbon within the project has been additional by looking at the trajectories of the two regions. A lot of this is very computationally intense. There's a lot of different data sets that go into this, including elevation maps, land use class change data, the project polygons themselves, country borders, which again are not a kind of decided data set. And all of this comes out the other end, but usually a number saying how much additionality there's been per year. So I want to talk a little bit about some of the problems that we encountered, and that started with the data itself. So one of the data sets that we use is the tropical moist forest data set from the European Commission, the JRC data set, which shows us land use class change. So land use classes here are looking at forests and deciding whether they're undisturbed, deforested, regrowth, degraded, water, or other. And that's shown by the colors. And this is used to kind of primarily as the source of additionality within the computation, because we can say for this particular region, undisturbed forest would have this kind of carbon density, and we can kind of multiply this and sum it to get an amount of carbon within a project. The problem is my colleague and I were working on this data and trying to produce numbers, and we were getting different numbers. And we were trying to work out why, and we tracked all the way back through the code, through other data sets, and about a week or 2 weeks later, we finally got back to this one in particular and noticed that actually we were using two completely different data sets. I was using one that we had downloaded within a pipeline, and my colleague was using one that someone had downloaded a year previously onto a shared computing resource. And we both downloaded from the same URL, from the same website that's hosted by the European Commission, and we assumed that this was actually the same data, and that was a bad assumption to make. The data on the left of the screen is from 2021, downloaded in 2021, and the data on the right is downloaded in 2022. And this is showing Indonesia in the year 2008. And hopefully you can see from the two data sets that they're not the same. There's a lot more orange on the right than there is on the left, and orange is deforestation. So unfortunately, this is actually a pretty bleak picture, showing that the calculation in 2021 wasn't quite right for deforestation, and in fact, there's a lot more in Indonesia than had previously been thought. In fact, the differences are quite substantial. If we look at deforested and the third row, we can see about a 3% increase between the 2 years. And just to reiterate, this is 2 years when we downloaded the data. This is not year-on-year change. This is simply for 2008, and the data set's changing, and we'll look at why the data sets were changing in a moment. But 3% might not sound like an awful lot, but in fact, it's roughly the size of Togo in Africa. So it is a substantial area, as Indonesia is quite a big place. And you can think about that there's a lot of downstream ramifications to some of these problems, depending on how you use this data set within your own work, within already published research, or in our case, within a pipeline, and trying to compare it with work that our ecologist friends had already done. But they weren't sure which data set they had used either. And so suddenly we're in this complete world of uncertainty, and we can't even check who's right, who's wrong anymore. That's not to say that this uncertainty is wrong in any way. We do update versions of things. We do make mistakes, and we do want to correct them, even retroactively. The main problem here is that the source from which we were getting them didn't version the data sets in any meaningful way that allowed us to check very quickly if we were using the same data sets or not. And nor did our pipeline kind of technology allow us to do this either. So here are just some of the reasons why this has actually changed year on year. For all very valid reasons, and they have a lot more details in their change log between these versions. So you might think there's uncertainty in the data, and that's something we can get a handle on. We have things like Git within computer science, we have version control systems, and maybe these don't scale to big data sets, but there's a lot of work in this area with things like Data Hub and all sorts of research to try and make this better. But just as we got a grasp on that, we suddenly ran into problems that the code is also not versioned properly within the operating systems or containers or whatever technology we're using to run the pipeline. And so this is an example of a geospatial library called GDOC. which has many, many different versions. In fact, we're now up in the region of about 3.8 currently. But it turns out we were using two different versions of GDAL, and for the same command line, we were getting different results. So here, it's a very simple example of running the terrain ruggedness index. What that exactly means doesn't matter too much, but the command lines were exactly the same, and here I've been a little kind and labeled the outputs differently. So we have bar 2 TIFF and bar 3 TIFF, but you can imagine this wouldn't be the case usually. And then we calculate the difference, and hopefully we would just see 0 everywhere because there was no change between this minor version between the two libraries. Of course, that wasn't the case, and the default algorithm had actually been changed between these two versions because they realized, again, quite rightly, that there was a problem, there was a bug, and the default algorithm was for underwater terrain, not terrestrial terrain. Most people using GDAL assumed it was for terrestrial terrain, and again, a bad assumption to make. And this caused a lot of problems. Of course, now that you've got your code uncertainty, you might think that we've kind of bottomed out. Data uncertainty, code uncertainty, that's pretty much all we do. But on top of that, we also ran into hardware uncertainty. And this is an example of just some optimizations that are made in floating point vectorized libraries that turned out to cause a lot of problems in very subtle ways. So we won't delve into floating point numbers entirely here, but you can imagine that floating point has to be in some way discrete. It's not that we have unlimited precision here. But it turned out once we put something inside an array in NumPy, it used a vectorized version of an operator, which had slightly different semantics about what was allowed in terms of precision. And then when we pulled it all out and tried to do this calculation where we subtract the two, which we thought were the same numbers, are not in fact the same numbers at all. And again, this is actually below some amount of precision that we deemed okay, which is fine for single operations. But when you accumulate these over a large number of summations, they actually add up into something quite significant. So this image is showing kind of a data set for biodiversity. And again, this isn't too important exactly what it's showing, except that the sea should be entirely yellow in this case, because it should be 0, because we're looking at terrestrial biodiversity and sure there shouldn't be any in the sea. But it turns out for these regions that were overlapping, we were accumulating all of these little tiny differences, and these were becoming significant over the course of the computation. So we've had uncertainty in the data, uncertainty in the code, uncertainty in the hardware. And I think an important point to make clear at this stage is that this all compounds, right? It doesn't just kind of sum, it gets worse and worse and worse. And it's very, very hard for us to even begin to start answering questions about what's the uncertainty in the ecology itself. The scientific methodology has uncertainty in it. Instruments have precision. Methodologies use sampling, all of these sorts of things. And how do we communicate between ecologists and computer scientists this level of uncertainty as well? And it turns out actually this is really, really hard. And there are tools to help make this more manageable, but we find even within our own interdisciplinary work that trying to communicate between ecologists and computer scientists, the methodology, both in terms of a narrative that maybe ecologists could understand, and then the precision that was necessary for concrete implementation was incredibly difficult. And so this is an example of a methodology we wrote for some of this additionality work, which on the surface looks incredibly precise and contains a little bit of narrative that helps explain it. But so far, you've also noticed that a lot of this work is incredibly visual. It requires maps, and there's nothing like that here. On top of that, this has all been done in a Google document, which doesn't have any kind of support for undefined variables or types to make sure that we're trying to add the same things within the code or in the pseudocode. And ultimately, this has to get somehow translated into a bunch of Python code that we run that is supposed to be the specification that we were looking at. And somehow this implementation has to be outputting results that we visualize that have some kind of meaning. And suddenly there's this thread that has to be tied the whole way through all of this. And at any point, a lot of uncertainty can appear. So we've got uncertainty in the code, uncertainty in the data, uncertainty in the hardware, and finally uncertainty within the communication between the interdisciplinary fields. And again, all of this compounds to the point that it's very hard to make any kind of precise statements about the results that we get out at the end. And it's very, very hard for us to communicate with, say, ecologists about the uncertainty that's happening from the computer science point of view, and it's hard for the ecologists maybe to communicate with us the uncertainty that they have about their own methodologies. And then we're not really sure if there's a lot of, say, variance in the results. Who's to blame? Is it the computer science uncertainty? Is it the ecology uncertainty? Is it some mix of both? And all of this ends up making our lives very difficult indeed. So that's a lot of problems, a lot of maybe our work isn't going so well. I think it's important then to reflect on like why are some of these problems the case? Like what has perhaps computer science research done to make it harder for some of these problems to be solved? And I think one of the things is that there's a relationship between computer science and other domains that's maybe quite unique, similar in some sense to engineering fields, but I think computer science is really entering its own realm of difference here. So I really like this quote from a group of researchers in Edinburgh who were looking at what it means to be a research software engineer in kind of the modern context. And they were kind of saying that no one with the same casual attitude to experimental instrumentation as many researchers have to code would be allowed anywhere near a lab. And I think this one really resonates a lot. And again, this isn't to say that anyone who is doing this kind of work is doing it wrong. A colleague of mine pointed us towards a paper which kind of coined this as the vernacular programmer, which is someone who has to code by the nature of the work that they're doing, but are domain experts, in fact, professionals in their own area, and are very, very competent. However, I think this statement still holds true, and it does worry us a lot. And we saw this within our own work when we asked, for example, ecologists, could you tell us what inputs led to this output? And we were pointed towards emails that might contain some of the CSV files. We were pointed towards shared computing resources, Google Drive, things that were only accessible on closed centralized platforms like Google Earth Engine, and all of these things, which maybe in the computer science world we would recognize as perhaps not good practice, but obviously within an ecology world, there's different deadlines, different priorities, and that's completely fine. So they go on to kind of make this distinction between researcher developer and research software engineer, which I think is an important one, because I think actually the line gets very blurry between these two, and often this is a real source of some of these problems within our work. And so the first one, researcher developer, I would say is what a lot of people in the room might be, who are wanting to do research and are using code to do that research. Whereas a research software engineer is someone who is kind of embedded within another domain who wants to help them primarily by writing code. And so they don't have the same kind of deadlines or expectations to meet from a research point of view. For example, publications, getting things into journals, writing PhD theses, and things like that. Whereas the researcher developer is allowed to think of these things. However, the problem is when these two things mix, we get different expectations, and the communication usually breaks down where, for example, in our work, the ecologists might assume that we have a lot of time to spend on maintaining some of the pipelines or the machines that are running, when in fact we don't, because we're trying to meet our own research ends. And so I think where this kind of spawns from as well, I think it's the nature of how computer science from a historical point of view has kind of come about, in that it's a very mathematical science historically, and increasingly has become more and more about engineering, and has kind of become embedded in nearly every discipline, I would say, in some sense. To go back to this idea of the vernacular programmer, I think it's interesting to look at how we also would like to communicate between one domain and computer science. They make this distinction that actually, instead of formally specifying everything, maybe everything doesn't need to be as purely mathematical and functional as computer scientists might want. And often within these other domains, that's just not the nature of the problem at all. And I think we see this a lot with the work that we do with ecologists, in that a lot of the programming is incredibly exploratory. The specifications that we generated, which ended up in a Google document, didn't just come out of nowhere. They came out of a lot of kind of exploring of data sets and writing programs in a very ad hoc fashion. Looking at some of the statistical analysis that came out of that, kind of revising these things, going back, rerunning them, and then finally writing a specification towards the end. However, our tooling generally doesn't support this kind of workflow. Within computer science, we're much more interested in things like unit testing, which is a very, very functional, we want to assert that this input generates this output. And once you can start trying to add in things like statistical checks there, that's not really how we teach computer science. In fact, I think in things like continuous integration pipelines, we're very much focused on just testing very small components with a very specified kind of algorithm that they should follow. And that's not necessarily the case in the pipelines that we want to generate for data science. So they came up with this term credentials instead of specifications within this paper, which I think is an interesting idea to think about, in that instead of trying to be formally correct about something, we can decide to be good enough, in the sense that a lot of this work within kind of experimental science is really looking at being just good enough and trying to get over some hurdle, rather than trying to be formally correct all the time. And then just to reiterate, I think a lot of our tooling has not been developed in computer science for the vernacular programmer, but is instead been developed for the professional programmer. And I think we see a lot of this in things like the Git version control system that we then try and supplant onto all of these other domains, and we find a lot of friction there. I think it's also in the way perhaps that we teach computer science. I think we focus a lot on the kind of mathematical theoretical side, but don't focus on perhaps some of the more important aspects for interdisciplinary work, like human-computer interaction, or data science, or how do we communicate computer science to non-technical experts or vernacular programmers. And I think these are kind of areas that we could look at in more depth. So that's kind of most of my presentation. I just want to thank a lot of different people, including my advisors, here are Neil and Ketchup, a lot of the colleagues in plant sciences and zoology who have dealt with a lot of the kind of growing pains of trying to do computer science within the ecological setting, including Tom Swinfield, and then also my computer science colleagues, particularly Michael Dales, who has gone through a lot of these problems with me, and some of the slides are thanks to him. And also my colleagues and office mates who have listened to a lot of these problems over the last couple of months and helped me kind of, find the right visualizations and find the right words to explain a lot of these problems, without which I wouldn't be able to make a presentation.
Thank you.
Yeah. Yeah, it's really interesting. There's a kind of gap. I work in the Turing. We have 65 RSD research software engineers there. Some of who came from the CERN team, some from the Human Project. Totally get what you're saying. They would be yeah. But there's a kind of cultural thing across different. I mean, you're obviously in this context talking about the ecology of vernacular programming versus computer science. But I was thinking two other examples. I was involved in regularly porting large Fortran code bases in the 70s. One from the National Center for Atmospheric Research in Boulder, Colorado, who's still around and stuff. They had the most amazingly cool test data that you had to, every time you went to your computer, by the way, not going from 32 to 64-bit machines, we're talking about going from 60-bit to 36-bit machines. I mean, really obscure stuff where numerical analysis, which we don't teach in computer science anymore, really mattered. Sensitivity, anything like that. But atmospheric physicists were really good at programming, and they were really a bunch of RSDs. They were like, fantastic. And they had the resources to fund that. That was the other really important thing. I mean, it's a positive story. The other story, I think people probably maybe from 3 years ago, there was a lot of doubt cast on a guy called Ferguson from Imperial who had this code that did a model of epidemics, predicted there was going to be a massive disaster if we didn't have lockdown, as it happens, probably correctly. And so we did lockdown a bit late, and it was less of a disaster. But people cast us massive aspersions on this code. And then there was a really nice analysis you can find public document from Microsoft, who actually got the code and went through and fixed it, but then said, actually, it wasn't that bad. It just needed a lot of tidying up. But in fact, had been maintained over a long period, and had been used to write lots of papers. In this case, was really important because it was providing a model which said what could happen in terms of number of cases that would need hospital beds and so on. So it really mattered. And then there was this problem that the doubt about it was overstated, and that created an actual problem for doing things. And of course, that's happened with climate and ecology as well. Yeah. So I think this is like really thorough. Like, yeah, the main point is really important to get this better, but we have some processes like you alluded to, which can help. And there are cultures which have and are doing it better, and the ones that clearly aren't. So yes, that's just what I wanted to say.
Thank you for your presentation. I think this will make a valuable contribution to the Unknown Science Conference. I have the bit about uncertainty of dependencies. One idea that I had while you were going through that is maybe part of the issue, the uncertainty, these kind of accumulating errors that cause a lot of problems, is that domain researchers will typically, like I have a cousin who does research in business. He's an entrepreneur researcher, and he has all these statistical models he uses R. And when I was doing maths as an undergrad, he's like, that's cool, you understand that, because I don't. I do my research, I have a magic box, I plug it in, it gives me my numbers, and then I go back. I think a lot of domain researchers relate to computers and to statistics in particular in that way, where they just sort of offload all the mental energy of really understanding it to someone else and just kind of trust some kind of interface specification. It seems to me like that relationship could be causing some of these problems because you have these layered dependencies that may have nuanced kind of errors that accumulate. So my initial gut reaction to that is that, like, boy, wouldn't it be better if everyone understood the statistical kind of ML models more thoroughly, which might be, impractical, and a lot of people relate to maths in unfriendly ways, and so that may not be something that's actually reasonable. That to me seems like, if that were possible, that could tame some of this uncertainty, and that is my gut reaction. In contrast to the point you made about vernacular programmers and maybe having computer science as a discipline kind of move more toward the others. I wonder, what you think about that.
Yeah, I think it's a good point. I think an understanding of the statistics of what we apply. I think the kind of black box model is usually quite detrimental to things like uncertainty. I think some of the problems here are for kind of different in the sense that, the system dependencies and hardware stuff is literally just people using computers, right? Which is kind of like, is the operating system or the model in which, we kind of have for operating systems just incorrect for people who just want to do this kind of analysis, right? For example, you can have all the nicest kind of like interfaces and kind of platform, domain-specific languages, all this sort of thing. But if you install GDAL 3.2 and 3.3, you're going to get different results, right? And I think, there's a lot of work in this area about reproducibility, projects like Nixos and all these sorts of things that are heading in the right direction. But again, there was a nice, article recently that kind of described these things, again, being developed for the professional programmer or someone who's already a computer scientist, right? I don't think it's fair to ask someone to install Nixos in order to solve their dependency problem, right? So I think there's work to be done in just how do we make computers more reproducible for anyone that's using them. Again, for example, a lot of the ecologists are using a shell, and a shell is kind of this beautifully mutable environment where you just make files and do all sorts of things, and you have no way of going back to kind of the previous state that you were in, and even the tracking of what you did is a little ad hoc through your flash history and things like that, which we tackled with, and my colleague Michael tackled with, which is where he had to go onto someone else's user account and go back through their bash history and work out exactly what files have been used as inputs and what files were now outputs. And you kind of look at all that and say, maybe we can do better there, but why haven't we? Perhaps because operating systems have been kind of historically designed to be for computer scientists or professional people like that. particularly the ones that we then use in kind of like big clusters that we then give access to ecologists. But I think your point still stands for things like actually, particularly for uncertainty within methodologies, where you're doing more statistical analysis or applying machine learning models on top of all this. I think a better understanding of actual things that we're doing can go a long way. And I think increasingly we're seeing that with both kind of things like data science being much more of a hot topic in the curriculums for undergraduate computer science, and also in fields like ecology and these things. They're getting programming lessons, learning R and things like that. But I think we can do better at kind of bridging that gap as well. I think it's not necessarily one has to go all the other way. It's probably meet in the middle somewhere.
Is like a solution just to recruit more statisticians to work with people defining these methodologies?
I think maybe the point John was making a little bit here is like also that you've now got an economic factor to all that, right?
Yeah.
Which is I have my kind of ecology group, and now I've got to hire 2 research software engineers. I think there's also the point that unfortunately, or fortunately for computer scientists, unfortunately maybe for research staff, there's not a lot of kind of financial reward for the computer scientist who chooses the research assistant role or the research software engineer role compared to going and working in places that can offer a lot more financially and also a lot more computationally and resources, tackle bigger problems, maybe even get better publications because of that. So I think that's another challenge that we have to overcome, which I think can be done by kind of inspiring undergraduates and things like that into these areas, into these really, difficult problems like climate change, and hopefully, I'm not going to speak financially about what universities can do, but I'm sure they can do something to maybe make that a little easier.
Just reminded me that when we started the Turing Institute, the kind of baseline document was a paper by David Donahue, who was like, MIT and Berkeley wants to write a syllabus on what should be taught for data science before we call it AI or anything else. And it's 2017 was the paper, the next 50 years of data science. And what it says is you need to train people who have got the equivalent of half of a degree in statistics, and half a degree in applied computer science, some maths, and then some human skills. And there's a bunch of other stuff in the paper, but it's worth looking at. So it's quite a while ago. And it was, I think it's sort of what we try and teach in data science modules here. But of course, we only teach like a small amount of a whole degree. Or this was intended to be entire cohorts of people that what you were just discussing, which would be really cool. And you have people either side of disciplines who, half of the other side, they're not just seeing the API, as it were.
Yeah.
Oh yeah, well, I was just hanging on to Derek's question, which is like, I feel like often with these kinds of subjects, what I'm seeing is, recommendations that place additional burden on the user, right? Which is like, use a Docker container, structure your code in this way so that it's usable, and like simply like given that the incentive structures and publication timelines are the way that they are currently, they don't do that, and that's fine. I don't think that they should, and it sounds like you're not recommending that they should necessarily without kind of meeting in the middle with a kind of that's like a top-down approach with some kind of bottom-up approach where the systems work for the user better as well. I just kind of wonder what the balance is, because this to me feels like a very unique perspective, because I feel like I always see this kind of top-down, here's what everyone should do so that their coding practices are better, and it just feels kind of ridiculous because it's not happening.
Yeah, I think that's a great point. And I think like the kind of one of the main words there is like empathy. For the end user or the vernacular programmer, whoever it is you're working with, collaborating with, that they do have deadlines, they do have existing workflows. So this talk itself isn't about, our research that we're doing in this area, but like one of the kind of guiding principles there is that there are existing workflows. People do use Python and R, and they're good programming languages and they can do things, but how do you, in a minimal way, impact existing workflows and try and incrementally solve some of these problems in a way that can help people without telling them, oh, by the way, there's this containerization technology called Docker, have you tried it? And they go, no, I don't know what you're talking about, nor do I want to know what you're talking about. I just want to be able to run my code, get a result, and run it tomorrow and get the same result. So if you could do something for that, that'd be great. And I think we have examples of that. One really good one, I think, in this is Google Earth Engine, right? For all the kind of woes that it may cause in terms of this big centralized kind of platform, Google could turn it off tomorrow and then suddenly it's the worst platform ever. It has got a lot of things right in the fact that dependency management is no longer a problem for the person who's programming in Google Earth Engine. They don't have to install anything. There's in fact, there's no operating system, there's no shell. It's just kind of the perfect environment from that point of view. It also ties code and data together really nicely. They live in the same place. And so you can very easily do a lot of exploration, but also you can export it and try and clamp it down to some amount of reproducibility. Of course, there's a little bit of opaqueness there in terms of what are they actually running? How much is it tied to Google's infrastructure? What if Google just turned around and changed some of the data sets that were being pointed to and you have no idea that that's happened? These sorts of things are actually really solvable, right? If we own the platform or whoever.
Yeah.
So I do think like it's not also to say that there's not a lot of good examples of things that can work, just that there's still a lot of work to be done, I think.
Right, and it's a little bit nerve-wracking to kind of outsource that to a company that's kind of doing it out of their own goodwill.
Yeah,
it certainly has. My understanding is that it's free researchers and has business applications. So they're making money off it. So the likelihood that they turn it off or stop making it free to researchers is low, but it still is concerning.
Yeah, and I probably wouldn't say that. Like I think that this particular company has a history of turning off big services, right? With very little
warning. Yeah.
So I think it's definitely the biggest worry. And in fact, a lot of our work here was how do we remove Google Earth Engine from the pipeline that was doing the additionality calculations.
Right.
And that's where we ran into problems like we want to use the accessibility data set. And it has very little documentation about where that's coming from, what extra like kind of post-processing steps that might be run on some of the raw data sets that are going into that. What version of all these libraries are they using, for example? Is any of this GPU optimized? Because also GPU versus CPU is not the same thing in terms of maths. Yeah. So there's all these sorts of problems as well. So I think it's not a bad thing to try and move away from it. However, I think from a kind of usability point of view, they've got a lot of things right, and there's a lot to be learned from for our own work.
Go ahead.
What fraction of these problems would you say it made computer science solutions?
Good question. Hesitant to, little hesitant to answer because I'm very aware of the kind of like technology will solve all of our problems kind of statement from a computer scientist. Which I think is why, and what's so interesting about this work is how collaborative it is. Like there was 3 months where I did just move around desks in the CCI, which is the Conservation Institute initiative, helping people with Git, right? Which is where you go, okay, Git is not the answer, right? Because I don't scale, or Michael doesn't scale either, right? And so it's interesting then to maybe go from that point of view and go, okay, well, here's a problem that we're facing, like version control as a thing seems to be the right idea, but this particular implementation isn't the right one. And there's lots of examples of other version control, but it's then asking the question, well, why haven't these kind of taken off? And so looking at those kind of like the negative spaces in there and trying to work out in collaboration with people who are going to use it, what the right models are probably the right approach. So I do think there's probably a role in all of it for technology, but so long as it's like really grounded in like, will this actually help you? For data dependencies and code and hardware, I think it's definitely computer science. I also believe the uncertainty in ecology has a computer science role, particularly in how we communicate. I think we've done a lot of work in computer science and how we communicate kind of specifications or ideas to people who are then programming them. I think one of the most successful kind of examples of this is the IETF's RFC kind of management system, which is how a lot of the internet protocols have been described and then implemented in various programming languages. I think what's more interesting there is more the organizational aspect of that, because again, I think it's very easy to write down specifications, but if we don't kind of agree on one common place to collaborate and to kind of incrementally improve or cross-reference methodologies and specifications, then I don't think it kind of gets that network effect that would allow it to be kind of this central place that we go to. But I think tooling around those sorts of things could really help ecologists explain their ideas and for us to implement them and then go back and forth there. Again, there's software that already exists to kind of do this, and so it's looking at that space of like, why didn't we use it, for example? Like, why weren't we aware of some of these tools? Why did we go straight to Google Docs to try and write ecological methodologies with a lot of maths and a lot of pseudocode? I think, you know, there's a lot of self-reflection to do here as well. I kind of think maybe this was a failure. You know, how can we do better? And I think that'll be interesting computer science research.
Do you think you're did you have a no? Dominic? Yeah, maybe Dominic. Yeah. No, sorry, man. Yeah. Dominic and then man.
Talking about uncertainty in a kind of side field, I've had lots of conversations with people who work in architecture, like actual buildings, not. They do this thing called, they call it design computation, where they program stuff and it generates buildings. And we've been having a sort of evolving conversation for a few years about uncertainty quantification and how they want to have that as part of the language, because they really care about what the variability of some components is versus what are the tolerances for other components. Like, I will allow this amount of give here, and you have these kind of bridging components, things like glazing spiders that deal with the variability, and they want to sort of be able to understand that.
Yeah.
And so the people there are saying, oh, it'd be really great if this was somehow part of the language, and you could sort of say, no, you can't put these things together because this vary too much and stuff like that, and have something like interval analysis at the type level or something like this. So we've been talking about this for a while, and actually there are a bunch of specifications about how you there are both a bunch of standards about how you specify different kinds of variability and uncertainty in this space. And I wondered whether there's a relationship here. You know, to what extent could we, again, this is like throwing a technological solution at things, but have language facilities for talking about uncertainty. Maybe you can't capture all of it, but I know what you think about that and having sort of first-class representation of it in the language.
Yeah, definitely. I think that's definitely something. I think people have looked into that as well, right? I think there is like some amount of research in this area. I think one big problem for this is kind of the complexity. It's something I haven't really touched on in this, which I think I should add, is that kind of introducing computer science into this area has also exploded the complexity of the methodologies. And so they're incredibly big and very kind of, you know, there's lots of different computations that need to happen. It's not just one program file, for example. Yeah. It's, you know, we start with downloading a bunch of data, and then we have to do lots of different analyses that we can do in parallel, because we're allowed to calculate the slopes from the elevation, and then we're allowed to, you know, kind of aggregate the land use class data and things like that, and then it all gets pulled into one area where we do some analysis, and then it splits out again, and kind of like tracking that across all of these computations, I think would be a challenge that you might not see if you're allowed to just like program, like, you know, my experience with type systems and these sorts of things, it works great when you're like one code base and it's all happening there and then, and not very computational, right? It's very, I mean, there's a lot of work in it to make a type system fast, but it doesn't have to do any kind of like big number crunching or any kind of downloading of data. But I think this is also another area in which, you know, how do we do exploratory kind of computing in this space when the data sets are so big? And I think there's ways to make kind of a first class within a language to do, you know, sampling and like kind of smart things like that allow you to get some idea about what's going on and maybe some indications about the uncertainty of things that gets propagated through. And even just a little bit of that could possibly be useful. And I think ecologists would like that sort of thing. I think any level of statistical kind of analysis that you can throw in would be great. So for example, in our work, when we're trying to compare an update we made into some of the final stages within this pipeline with previous kind of results, we needed a bunch of intermediate statistical analysis of the different data sets that we were using to go, you know, when we did this counterfactual pixel matching, what were the standardized mean differences of all these matching variables? That wasn't actually an output of the code, because we only cared about, you know, say the actual amount of carbon stock. So we wanted to lift these things out of like in the middle of the computation to be able to say, we're going in the right direction here, where we've aligned on something, and that's great, or we haven't, and why? And then we generated the distributions of these things, and then went, oh, we're way off, and it turned out it was because I made a mistake somewhere, and it was a bug. But we could only do that via looking at intermediate data. So one thing we explored in this pipeline was very simple kind of visualizations for all the intermediate results, purely based on, looking in a directory and saying, oh, there's geospatial files in here. What if I just visualize them? Oh, there's CSV files in here. What if I try to compute some of the standardized mean differences for variables? And then what is the user interface that would allow both ecologists and computer scientists to sit down and look at these things and give some kind of semantic diff between one version that ran and then the next version that ran. And then you could have some kind of report that said, oh, your changes, haven't actually changed the results too much, and have only made it faster, for example. And that's often what we're doing. We're trying to optimize the pipeline. We're trying to say, we want this part to run faster without breaking everything. And at the moment, we don't really have the tools. And I kind of alluded to that a little bit, which is that I think from the computer science side, we're very focused on things like unit testing, a very functional kind of approach to, is this correct or not? And that's just not the nature of this kind of experimental science, where it's kind of like much more vague and much more statistical whether something is correct or not. And so we can make better tools for that as well, I think, and maybe make it a first-class feature of a testing library, or even better, maybe the programming language itself.
I think Maddie was.
You mentioned, or you had a comment earlier in the presentation about the ways that ecologists were not quite understanding some of the computational elements or the computer science components. And I'm curious, based on this work, but also your work in general, if there have been particular areas that have stood out to you where computer scientists are not understanding the ecological components, or things that you would flag for people who are working on ecology questions.
Yeah, I think that's a great question, and it reminds me of this kind of other looming question is like, who's leading the research anymore? Are ecologists leading their ecological research, or are the computer scientists leading it? Because there are points in our kind of specification where we've made decisions based on what is computationally efficient to do, rather than what is the idealized ecological, this is what we would actually do, like we would do it for every pixel in this country versus some sample of that pixel. And I think from that point of view, the computer scientists, we didn't understand why that decision was made, nor did we understand maybe the ramifications for any kind of uncertainty that that introduces, because that's not maybe our area of expertise. And we definitely didn't understand that it was computational limitation within the methodology. And in fact, a computational limitation of what Google Earth Engine could do within that methodology. So I think that's an interesting kind of point that's similar to what you were asking. I think there's a lot of points, and I think this comes back to how we communicate these things better, that, computers, we are never going to be ecologists, try as we might. And I think having better ways and mediums to communicate between the two fields is an area that would allow us to do good computer science without having to understand too much ecology. Because the ecologists can describe their methodologies in a slightly more precise, slightly more mathematical way. And again, it's this kind of bridging the gap between the two, without forcing either one to have to basically learn an entire new field and move all the way over. And fortunately for us, we have quite a few people who kind of already do that. For example, Tom Schoenfeld is a very, very competent programmer. So it's fine for us to explain some of these things. And likewise, I think like Michael is getting better and better at ecology, and can do this as well. So there is a place for having people who are, just nearly experts in both. But I think we can do better from a computer science software point of view to help bridge it.
Question over there. Did you have
When you gave the example of error propagating from the floating point minus, is there like a specific floating point minus operation in Python that you weren't using, or was this inherent in the precision limitation?
Yeah, so this problem arose particularly Michael knows more about this than me, but this arose a vectorization math library. So once you put something in an array in NumPy, and then you try and do some overloaded operator on it, it then kind of recognizes this is actually an array, and so I'm going to vectorize it and make this power function use a slightly different one than the one perhaps you thought it was using. So if it's just a normal number in Python, it uses Python standard library exponentiation. And then this one was using the NumPy one. It happened to be running on a particular architecture that had a particular semantics to what that the level of precision that was allowed within these vectorized operations. And then finally, when the two numbers are just subtracted, they're not actually the same numbers anymore. So it wasn't, again, it's this level of like, who's supposed to understand this problem? Even the computer scientists were like, whoa. In fact, it was raised as a bug, and then the NumPy people were like, it's kind of expected behavior. Like, of course, this is a little annoying, but like, it's not our problem, and which is fair enough. You know, this is a particular architecture of computer. It's a hardware kind of problem, and so it's not really on them to fix it. It's on us probably to put the right checks in place for this kind of thing, but we weren't even aware of that. I'm not sure how long it took Michael to find these problems. It only really arose from the fact that they wanted to do some like analysis in a world where all biodiversity or something like that was destroyed, right? It was just kind of like, what would our calculation be in these edge cases where we set everything to 0? And it's like, we expect everything else to be 0, and then it wasn't quite 0. And suddenly it's, yeah, that's where the analysis came out of. So again, it was only caught by the nature of people exploring this, rather than any kind of tests that were set up, or even the output results of the very first computations that were coming out. I don't think the problems were seen there.
What you really need is some kind of digital public infrastructure that's the equivalent of, again, multiple lenses, like continuous integration of future notebooks, except with the distributed over lots of different skill sets over the world. So when somebody shows up, it's a floating point problem with a way the assumptions are made in a given program. Now, this set of skills over here get notified. This is kind of, then it's a ecological modeling error. And then this set of people. No, but I'm not really joking. And this kind of you want a digital public infrastructure to get away from the Google owning it. Somebody decided to charge you money for it, so you pay that. And it's this whole area you're working in is something where, unlike if you're doing something for precision engineering with the Rolls-Royce, there's plenty of money for it, so you will get lots of RSPs, but you know, and you get people with the different skills. But it's a very narrow problem. It's the breadth that's really killing you here. Yeah. It would be really interesting to figure out if we could persuade a funding agency to pony up, you know, the doing the Google thing, but owned by everyone. Yeah. And sustained. That's a crucial thing. I think, in fact, not just sustained, but be growing. So you just add in more and more people who have an interest, have some time. It's not just that open source thing, but it has value. It's just the time scales of things where shareholders get their money this year. You know, but we could one day just tap the people.
You want a portable stack exchange, basically. Something like stack exchange. Right. I'm not joking. I mean, stack exchange does exactly tap into this. Yeah, but also ecologists and stack exchange. You want ecology stack exchange with some RSCs and some program. Anyway, but I had a couple of observations, I think, maybe various questions just to end. I think one is that what do you call uncertainty, I would call it under-specification, in the sense that they did out change, right? But they didn't specify how they changed, what they changed exactly, right? It's like this common problem. You upgrade your software, upgrade your operating system, and then it doesn't work anymore. You say, why did they change that? But because under-specified what those changes are going to be doing. It's a under-specification problem. And more broadly, the under-specification from the computational side to the ecologist side, I can say that, you know, when you want to work with people outside the computer domain, like when I started working with ecologists as well, when I started putting together the document, I asked a very simple question. I said, what's the input and what's the output? Because that to me is how you specify. There's the inputs, these are the outputs. And you know, they didn't understand what I was talking about. Like, what do you mean inputs and outputs? I said, what data sets do you use as your input and what does it produce? And it took almost a month of talking for them to understand the meaning of input and output and the algorithm, right, that goes in between. And so and secondly, assumptions. What assumptions are you making in your code? So the document is very heavy in assumptions and very precise in inputs and outputs, because without that, you don't even know what you're getting, right? And ecologists don't have that sense of computational thinking, at least the ones I work with. Maybe eating is different. Maybe ecology in the room. But I mean, do you guys learn about input outputs?
Yeah, I think it was interesting during that process of doing the methodology, and when we were asked to write down assumptions. I think for us, at least for me, thinking about this question is not that we're not aware of assumptions, but we're not aware of which assumptions were asked for by the computer scientists. In that there are loads of ecological assumptions that are there, but which of them are relevant that should be specified explicitly in the code when we're doing the coding. And I think it's probably because that we're really used to an intrinsically vague, complex, messy system. That for us, a lot of the imprecision there is kind of just permitted. So that's so I guess that's why we don't think of for us, that one decimal, it will be just like the one decimal difference when we measure tree diameter. So it's just something that's supposed to be there. So we don't see that it's hard for us to understand how structurally, when you do it in the computer science program, it's like some of those can suddenly be propagated into and blown completely out of proportion. So I guess that's my my perception at the moment of from the ecology point of view.
Jacob is also sort of a ecologist in training, sort of. Maybe what do you think about that?
I guess so. I did natural sciences, and so we had very elementary introductions to programming, like how do you do a linear model? We didn't have anything about good coding practices or version control or anything like that. I guess I was going to maybe ask, do you think there's been more formal programming teaching for ecologists or about natural sciences in general?
Sure. Yeah, I think so. I think it can't be kind of relied on kind of as the only thing. I don't think it's, because I think you get this problem. It's okay, now you need 2 degrees. You need your natural sciences degree and you need your computer science degree. You can't rely on that. But I think coding practice and software engineering, those sorts of things definitely has a role to play. And I know that and increasingly more and more, it already does play a role. I think collaboration between, for example, the computer science department and other departments would be great. And obviously we do that, with most of you being AI for ER and having collaborations, myself being part of the CCI and things like that. But I think even from an undergraduate point of view, it's kind of it would be nice to foster that more. In both directions, I think, right? It's not just that everyone else needs to learn computers. I think computer scientists need to learn about other disciplines and form, again, that kind of empathy towards other disciplines, because at least in my experience, when you come out of doing computer science, you then just go and work with a lot of people who are not computer scientists. So I think, my undergraduate certainly didn't prepare me for that. So I think there's work to do there as well.
There's a historical inevitability thing that people think something was done, and so they stopped teaching it. And I did natural sciences, and I was taught numerical analysis by Frank King, who was in computer science department of a computer lab back in the day. And so we got not just programming, but actually writing from Fortran programs, but using NAG library and other libraries that had really cool, complicated matrix operations. You had to know about whole conditions, blah blah blah, and it was. Wow, and I don't think that's in any science course anymore. But that's a disaster, because now we've gone back and there's NumPy example just now, which actually would have sort of stared somebody in the face if they'd done natural sciences and then were doing some eco programming and saw that, thinking, that's probably that. But the thing I remember reading about that was taught by Frank. Well, something, but then people chart faster. But these things get forgotten because they're. It's that must all work. It doesn't, because
Okay, we are running past time, so let's thank again. Right, so we may possibly not have a speaker next week, so we'll touch upon it. If anyone wants to talk next week,